We are going to learn physics at this time because I think there was a technicality that happened, but we can always work it out. So we are going to do physics this time, then geography, you can do it afterwards, maybe in the afternoon. You will be advised by the form mistress. So welcome to today's lesson. Allow me to share the screen. So last, in the previous lesson, we learned about some terms, which I want us to remind ourselves quickly, then we proceed from there. We learned about angular displacement, and we said that it's the angle described at the center of a circular path, denoted by theta, which is given by S/R. We also learned about a radian, and we said that if that angle, the angular displacement described at the center of a circle, given by S/R, when S equals to R, then the angle is 1 radian. Then we talked about angular velocity, which we say that it's the rate of change of angular displacement, which is theta over time. And we also looked at various formulas involving angular displacement. One of them being V equals to omega R, therefore omega is V over R. We also talked about angular displacement, angular velocity as 2 pi over T, and also 2 pi F. After that, we talked about centripetal acceleration, which is A equals to V squared over R. Then later on, we talked about centripetal force, and we said that it can be expressed in 2 ways. One is mv squared over R. The other form is m omega squared R. So the factors affecting centripetal force are, one, mass of the object. So when an object has higher mass, then it requires a lot of centripetal force for it to maneuver around a circular path. Then the second factor is where we are told that increase in angular velocity causes an increase in centripetal force required to maintain this body in a circular path. It's very easy for a lighter vehicle to negotiate a bend, and for a heavy lorry to negotiate the same bend. That is for when it comes to mass. Then if we have two vehicles, one moving very fast, another one moving very slowly, it's very easy for the one moving very slowly to negotiate a bend. But the one that is fast requires a higher centripetal force. That's why we have speed limits at every corner of a road. Then radius of the path, we have some roundabout, others are very huge. So it's very easy to negotiate a very large roundabout because the centrifugal force required is very small. But it's very difficult to negotiate a bend at the same speed of a smaller roundabout. So those are the three factors: mass of the object, angular velocity, and radius of the path. It's expressed here in formula. So now we look at examples. Examples of uniform circular motion. Number one is a car rounding a level circular bend. So here we have a photo of a vehicle that is negotiating a bend towards the right. So the forces that are acting on this car, those forces are the action force, which is the weight of the vehicle, the reaction force. We also have the force of friction, which provides the centrifugal force towards the center. This arrow pointing towards the center is centripetal force provided by friction force. So this is the animation of the forces acting on the vehicle. N sine theta is yes, Bwana Wachira. Can somebody tell me whether I'm clear or not? My internet is unstable a bit. Somebody to just confirm that I can be heard, I'm audible. Okay. So let's proceed. So I was talking about the forces acting on this vehicle. And I was explaining that this horizontal force is N sine theta. It's the same as the centripetal force, which is N sine theta. Action force is mg. And then we have reaction, which is N. But since N is not in the correct position, we do what we call resolution of forces. To resolve a force means to change its position to a different position. So we resolve the reaction force from this position to the vertical position. So it becomes N cos theta. So this is reaction. This is centripetal force, then action. Let's hear from some students with questions. Hello. Yes, Mandela.
I've not understood the n cos theta and n sin theta. So I'm requesting if you could pardon.
Okay. Let me do so.
Yes.
I'm saying that n sine theta is the force that retains this vehicle in a circular path, which is a centripetal force. Basically, it's a force that is provided for by friction, n sine theta. Theta, remember, is the angle of inclination of this rod. It's called the banking angle. When you look at this rod, it's raised. At some point, you can see that it's raised on this outer side. It's called banking. So rod banking is simply the gradual raising of the rod on one side so that it assumes a saucer-like shape. So that angle of banking is the theta we are talking about. So just from mathematics, the SOHCAHTOA, we have this force directed to the center of the circle is given by n sine theta. When you do sine theta opposite of adjacent, you'll find that opposite of hypotenuse, you'll find that this horizontal force is given by n sine theta. When you do this opposite side, which is the vertical side, cos theta, which is adjacent of hypotenuse, you will find that this vertical force is n cos theta, which is equal to mg. N cos theta equals to mg. Mute your mic unless there's somebody who has a question, you raise up your hand. So this banking of the road prevents this vehicle from skidding. That's why we bank it that way, so that even if this vehicle speeds, it is prevented from skidding or moving away from the road. So when we come here, the forces are the same. You can see the road very clearly banked here. Here it's banked on the left, and then here it's banked on the right. So you should know what is road banking. Gradual raising of the rod on one side so that it assumes a saucer-like shape. Okay. Now here, we are told that n sine theta, which is the centripetal force, is given by mv squared over r. N cos theta is the reaction force, which is equal to mg. Therefore, tan theta, I think from trigonometry 2, we learned that tangent of an angle is the same as sine of the same angle divided by cosine of the same angle. So tan theta equals to n sine theta over n cos theta. I hope that is clear. Tan theta equals to n sine theta over n cos theta. That is friction, centripetal force divided by reaction. Substituting, we will have mv squared over r divided by mg. So mv squared over r divided by mg simplifies to v squared over rg. When we divide this over this, we get v squared over rg. Therefore, v squared equals to rg tan theta, and hence v equals to the square root of rg tan theta. So don't cram all these things here. This is just to show you the derivation. Of course, know the forces. We have the centripetal force, reaction, action. Those are the three forces, but you don't have to cram them. Nobody will ask you to show because it's not in the syllabus. What you need to know is, how do we get this critical speed? This is the critical speed. So when you reach a corner of a road and you see 30, a very big sign written 30, that's called critical speed. And you're not supposed to exceed that speed. If you do, then the vehicle skids out of the road. Now, how do we define the critical speed? This is the maximum speed at which a body can move round a circular path without skidding. Maximum speed at which a body can move round a circular path without skidding. So any speed below that is okay. Above that, the car skids out of the road. Factors affecting this speed are the ones written here. We have radius of the bend. Radius of the bend matters. If the bend is so pronounced, then the critical speed is also low. If the bend is not that sharp, the critical speed is also high. Conditions of the tires and nature of the road, because this one enhances friction force. Then we also have angle of banking of the road. So once you are able to remember this formula that critical speed equals to rg tan theta, then these are the factors: radius of the bend, angle of banking, and of course, the frictional force, which is given by conditions of the tires and nature of the road. So those are the three factors affecting the critical speed. Example number 2. As I said, don't cram these things. You only need to know that v equals to the root of rg tan theta. So this is a bicycle. This is a bicycle rider. What are the forces acting on him? We have the action force, which is mg. We have friction force towards the center of the circle, Fr. We have reaction force. So here we apply the principle of moments. We can see theta here. Theta is the angle between the bike and the vertical line through the center of gravity. So clockwise forces equals to anti-clockwise forces. The clockwise force here is this one here, the reaction force, clockwise. Then anti-clockwise force is the friction force here. So R multiplied by distance from the pivot is this distance here. I don't know if you can see X. X has been written down here on the yellow line. This is X. So reaction multiplied by distance to the pivot, which is X, equals to friction, which is anti-clockwise, multiply by distance to the pivot, the vertical yellow line. So Rx equals to Fy. Then we now divide friction and reaction. Friction over reaction equals to Xy, and we know friction is the one providing centripetal force. Therefore, friction is mv squared over r, and reaction is mg. Substituting, we get x over y equals to v squared over rg. And from trigonometry, we know the tangent of this angle is opposite, which is x, over adjacent, which is y. That is from SOHCAHTOA. Tan theta here is opposite over adjacent. Therefore, tan theta is x over y, which is the same v squared over rg. Therefore, v equals to the root of rg tan theta. Now, friction is also from Newton's third law of motion. We say that friction equals to the coefficient of friction, mu, times reaction. So, instead of writing here mv squared over r, our substitution level here, we are going to write mu, then mg. So when we have mu mg divided by mg, then we are left with tan theta equals to mu. So the tangent of this angle that this person is bending with should be equal to the coefficient of friction, or it should be less than that. The tangent of this angle should be equal to the coefficient of friction or less than that. Otherwise, anything more than that, the bicycle skids out of the road. But again, the critical speed for this person to be able to maneuver that bend is given by rg tan theta. Depends on the radius of that bend, angle of inclination of the bicycle, then we have the condition of the tires of the bike and the road. So what you need to know from here are two things. V equals to the root of rg tan theta, and friction equals to, tan theta equals to the coefficient of friction. What you need to know from here, the previous one, is V equals to rg tan theta, and also know how to define critical speed. The rest you will not be examined. Now, another case, practical example, is aircraft banking. This is a case where for a plane to turn, to change direction, it must be inclined. So when an aircraft is making a turn, the aircraft must roll to a banked position so that its wings are angled towards the desired direction. It does not just change on a horizontal position. It must change. And also the speed of the plane equals to rg tan theta. The last example is a conical pendulum. So here, this is a pendulum that is being rotated in a circular manner, creating something like a cone. So it's attached up there, then inclined at angle theta. Of course, we have tension force in the string. Then we have the other forces acting on it. We have the centripetal force given by T sine theta. This is centripetal force. Force pushing it towards the center of the earth or the center of the circle so that it maintains that path. We have the action, which is mg. When we resolve T, resolution of forces, when we resolve T to the vertical position, it becomes T cos theta. Then, of course, tan theta equals to V squared over Rg. Then, making V the subject, we get V equals to the root of Rg tan theta. So we are told that when the angular velocity omega increases, the ball rises. So this system is used in a manual speed governor. We have two types of speed governors of a vehicle. We have electric one and we have a manual one. So this is a manual speed governor, especially used for heavy trucks. It's connected to, it works using the principle of a conical pendulum, which is connected to the fuel supply. Therefore, it's able to either cut off or reduce the fuel supply. So those are 4 cases, but you don't need to know the derivation method. You just know the formula. V equals to Rg tan theta, square root of Rg tan theta. Know the factors affecting that critical speed. Know that tan theta for the bike, tan theta equals to coefficient of friction. Only that. Now we move to vertical motion. So vertical motion, as I said in the previous lesson, is motion that looks like this. Here, we have a merry-go-round which is in vertical position. This first diagram here, the first photo, or this one here in the second diagram, this one, vertical motion. We are not talking about this one. This is horizontal. We are talking about this one. So we need to investigate the tension force, which provides the centripetal force, because if that string cuts, this is like a stone tied on a string, then being whirled in a vertical manner. Therefore, it is the tension force that retains this circular path. So at position A, the tension force T is given by mv squared over r minus mg. At position B, which is the lowermost part, the tension force is given by mv squared over r plus mg. That means tension at B is higher than tension at A. Because this is plus, this is minus. At position C and D, because the stone is not being affected by, the tension is not being affected by the weight of the object, because you can see the weight is acting downwards, but tension force is towards the center of the circle. Therefore, we neither add nor subtract mg. It's just tension equals to mv squared over r. Just like in a normal horizontal motion. Somebody may ask, why minus and why plus? Let's look at the two forces acting on this body. One of the forces is mg. The other force is centripetal force. So we can see that both are acting in the same direction at position A. Both mg and centripetal force in purple are acting in the same direction. Therefore, centripetal force plus mg equals to tension. Centripetal force plus mg equals to tension because they are acting in the same direction. And we know centripetal force is mv squared over r. So mv squared over r plus mg equals to tension. Sorry, it's supposed to be centripetal force Fc equals to tension in the string plus mg. Sorry for that. Centripetal force Fc equals to tension plus mg. Therefore, mv squared over r equals to tension plus mg. Therefore, tension equals to mv squared over r minus mg. That's why it's minus here. When we go to B, we can see that weight is acting in the opposite direction to tension. They are opposing each other. Therefore, we can say that centripetal force Fc equals to tension minus mg because they are opposing each other. So mv squared over r equals to T minus mg. Therefore, T equals to mv squared over r plus mg. So down here we add, up here we minus. C and D is just mv squared over r. So when you're asked which position do we have the highest tension in the string, then you say it's position B, or the lowermost position, bottommost position. Reason being, we have the centripetal force plus mg. And this is the position where the string is likely to cut or snap. So you can also be asked, state the position where the string is likely to snap. Then you say position B. Explain, this is the position where tension in the string is highest. Now remember, centripetal force can also be given as m omega squared r. So instead of mv squared over r, you can also use m omega squared r plus or minus mg for A and B. So before we come to application, let me share some questions on the same. Let's do some 2 or 3 questions, then we come back. Okay, so I think on your screen you can see some questions there. These are explanation questions. Let's go to calculations. Question number 2. A stone of mass 450 grams is rotated in a vertical circle at 3 revolutions per second. If the string has a length of 1.5 meters, determine the linear velocity. So what you do, first of all, you get angular velocity, which is, look at the quantities given. We have the revolutions per second, which is friction, not friction, but frequency. So you say angular velocity omega equals to 2 pi f. So 2 times pi times 3. 3 revolutions per second is the same as 3 hertz. So 2 times pi times 3 gives us 18.85 radians per second. 18.85 radians per second. Then we say the same omega equals to V over R, or V equals to omega R. So 18.85 times radius is 1.5. Gives us 28.27 meters per second. So the answer to Roman 1 is 28.27 meters per second. Roman 2, the tension of the string at positions A and B. We start with tension at A, TA equals to mv squared over R minus mg. Or you can use m omega squared R minus mg. So the mass is 450, changed to kilograms. That is 0.45. Velocity is 28.27 squared. Radius is 1.5 minus 0.45 times 10. So we're going to have 0.45 times 28.27 squared divided by 1.5. We get 239.76 minus 4.5. The answer is 235.26 newtons. That's the tension at A. Tension at B, TB equals to mv squared over R plus mg. So we shall have our mv squared over R gave us 239.76 plus 4.5. So 239.76 plus 4.5 gives us 244.26 newtons. That's the tension at B. 244.26 newtons. At A, 235.26 newtons. So that's how you approach that question, which is very common. We can quickly look at number 7, then look at a graph, then back to applications. A lead shot of mass 40 grams is tied on a string of length 70 centimeters. It is swung vertically at 5 revolutions per second. That's the same as 5 hertz. Determine the periodic time. So you say periodic time T equals to 1 over F, which is equal to 1 divided by 5. That is 0.2 seconds. Roman 2, angular velocity. So omega equals to 2 pi F, which is 2 times pi times frequency is 5. 2 multiplied by pi multiplied by 5 gives us 31.42 radians per second. Roman 3, linear velocity, V equals to omega R. So our omega is 31.42. Our radius is 70 centimeters. Change to meters, that will be 0.7 meters. The answer is 21.99 meters per second. Then lastly, maximum tension in the string. So maximum tension is at the lowermost part. So you will say tension T equals to mv squared over R plus mg. So that is 0.04 for the mass multiplied by 21.99 squared divided by 0.7 plus mass is the mass is 0.04 times 10. So that's going to be 0.04 multiplied by 21.99 squared divided by 0.7, we get 27.63 plus 0.4. The answer is 28.03 newtons. So the maximum tension in the string is 28.03 newtons. Okay, let's move to before the graph. We have this part here. The diagram below shows a mass M, which is rotated in a vertical circle. The speed of the mass is gradually increased until the string breaks. Of course, the string will break at this position. The string breaks when the mass is at its lowest position A and at a speed of 30 meters per second. Point A is 5 meters above the ground. Show on the diagram the initial direction of the mass at the point the string breaks. So you will draw a tangent here, a straight line, either pointing to the right with an arrow or to the left with an arrow. That's the direction followed by the mass. So either to the right or to the left, a tangent. Then to the path of the mass from A until it strikes the ground at position B. You will draw what we call a trajectory. In linear motion, we drew a trajectory, which is an horizontal projectile motion. So this mass follows that trajectory like that until it strikes the ground. So you just draw a curve like that, then strike the ground. B, calculate the time the mass takes to reach the ground after breaking off. So you will use the formula H equals to a half GT squared. Our H is 5 equals to a half times 10 times T squared. So T squared equals to 1 and T equals to 1 second. So time taken for the mass to strike the ground from here is 1 second. Roman 2, calculate the horizontal distance the mass travels before it strikes the ground. The range, you find the range. So you say R equals to UT, and our U is given as 30. I think we can see that the speed is 30. So 30 multiplied by time taken is 1 second, we get 30 meters. That's the range. Roman 3, the vertical velocity with which the mass strikes the ground. We can use the first equation of linear motion, which says V equals to U plus GT. V equals to U plus GT. The reason why it's plus is because this mass is moving towards the center, towards the ground, so towards the center of the earth. So plus acceleration due to gravity 10. So V, final velocity, equals to 0, which is initial velocity, plus 10 times 1 second. So the answer is 10 meters per second. Strikes the ground with 10 meters per second. So that's how you approach this question. It's a combination of uniform circular motion and linear motion. Now, suppose you are given a graph, because you can be given a graph that looks like this. The graph below was obtained when an experiment to investigate the variation of the centripetal force F with the radius R of the circle on which a body rotates was performed. So we can see the force against radius. So radius was being changed. Then the centripetal force measured. So it was done several times, and this is the straight line that was obtained. So every straight line assumes the equation y equals to mx plus c. So here we are told from the graph, determine the angular velocity omega of the body, given that mass m equals to 100 grams and F equals to m omega squared r plus c, where c is a constant. So we are asked to determine omega. So when you link this equation to y equals to mx plus c, what do you get? Let's link it. So we have F equals to m omega squared r plus c. Underneath that equation, you write y equals to mx plus c. Then we find out what is on y-axis. So F cancels with y. What is on x-axis is r. So x cancels with r. What are we left with? We are left with m omega squared. M omega squared, which is equal to the slope. Down there, we are left with the slope, which is represented by m. C is y-intercept. We all know that C represents y-intercept. So the value of C is, you read the value here, which is, to me, is 0.3. So C equals to 0.3. Although we are not asked about that. So 0.3 newtons. Let me respond to Larry Buru. Let's listen to Larry. You can. Yes.
I was asking.
Yes.
Pardoning or not, you just said. On the y-axis is when you use. On the y-axis is when you refer to force. And then on the x-axis is when you refer to the radius.
Yes.
So if you are to equate, that's when you cancel it off, not when working it out.
When you cancel?
When you cancel them off, it's to be able so as to be able to be left with the figures that are not involved in the equation. As in, you'll be able to remove force and radius by comparing.
Yes.
Right.
I'm saying the reason why I'm canceling is I want to know what is representing the slope in this equation that I've been given. So y equals to mx plus c, I know y represents the quantity that is on y-axis or vertical axis. Then x represents the quantity that is on the horizontal axis, which is radius in this case. So the reason why I'm canceling is I want to know two things. Which quantity is representing the slope and which quantity is representing the y-intercept? Because in most cases, you will be asked, find the value of omega and find the value of c. So my canceling is just to show that this represents this represents this. So whatever that is left represents each other in both equations. That's why I've said that m omega squared, which is left, represents the slope that is left in y equals to mx plus c. Then c represents y-intercept. So I hope you have been answered. If I have not answered, raise up your hand again. Okay. So we proceed. We have said that C is 0.3 newtons. Then we now calculate the slope. You look for 2 points. By looking at that diagram, I can see a very perfect point, 0.2 and 0.2. 0.2, 0.2. That's one of the coordinates I can see that will not give you problems. I can see another one, 0.5 and 0.6. So I have two coordinates, 0.2, 0.2, 0.5, 0.6. Let's listen to Korir. Korir, I don't know whether he's still there. He has disappeared. Just raise your hand again so that I can see you. Now, my slope equals to change in F over change in R. So change in F is 0.6 minus 0.2. Change in R is 0.5 minus 0.2. That gives me 0.4 over 0.3. 0.4 over 0.3, which gives me 1.333 newtons per meter. Yes, Victor?
0.2 na 0.2 hazipelekani.
Oh, wait, let me see. Oh, okay. Yeah, I've noted that. Let me change. So we have 0.1, two boxes represent 0.1. Therefore, this is 0.15. Let's make that correction. 0.15 and 0.2. 0.15 and 0.2. I hope that's clear now. Then we also have 0.5 and 0.6. I think that's okay. So that we have now 0.6 minus 0.2 over 0.5 minus 0.15. So that gives us 0.4 over 0.35. So when we divide, we are going to have 0.4 divided by 0.35 The answer is 1.143 newtons per meter. 1.143 newtons per meter. Then you come back to the formula and say m omega squared equals to 1.143. And m is given. If you look at the question down here, you will see that m equals to 100 grams. So you come and substitute 0.1 omega squared equals to 1.143. Yes, Larry, you can speak.
A question on the scale.
Yes.
Is it every 5 small boxes representing 1 on the x-axis of every 10 small boxes? Because if you use the values you said, 0.2, if you look at from 0 to 0.1, it looks like it's 10. So that 0.1 to 0.2 is another 10, which will give you 0.25 on the y-axis.
Okay, let's move together. Let's start from 0. After 10 small boxes, we have 0.1 here.
Yeah. Yes.
Okay. Then after another 10, we have 0.2, correct?
Yeah.
So this middle line represents which value?
0.15. Oh, okay.
Yes, that's what I've done. Sawa.
Yeah, thanks.
Aya, karibu. So we are now substituting, and I've said that 0.1 omega squared equals to 1.143. So we divide both sides by 0.1. So omega squared equals to 11.43. We square root 11.43. We get omega is 3.381 radians per second. 3.381 radians per second. So in the event that you are given a graph, that's how you interpret it. We have even other graphs that will ask you about R. Others will ask you about mass. So just compare the equation given to y equals to mx plus c. So back to our applications. As we can see here, the first application is a centrifuge. And a centrifuge is used to separate particles in suspension in liquids of different densities. For example, milk and ghee. When you look at the photo here, this is a centrifuge. Though this is not milk and ghee, this is separating two liquids. We can see a yellow liquid and a black one. So it means when we place this test tube inside here and switch it on, it's going to rotate at a very high speed. And as it rotates, these tubes are going to rise up. They will rise up to a horizontal level. So lighter particles will move closer to the center of the circle. That means they rise up in the test tube. Yellow liquid is lighter. Then the denser ones, which need a lot of centripetal force, will remain at the bottom because they require a lot of centripetal force. So this is how a centrifuge works. Ghee can also be separated from milk in the same way. So when you go to dairy farms, you will find huge centrifuges there. They're used to make yogurt, butter, and all that. Another application is merry-go-round and roller coasters. We can see them here. They are not just randomly constructed, there are some measurements that are taken. We need to know how much centripetal force is required. Then, of course, we must have very serious safety precautions. Seat belts, as you can see here, these people are very well buckled because of the centripetal force. If not that, then you fly away from that roller coaster, because there's a force that is required for you to maintain the circular path. The same happens to this vertical one. Precaution should be there. Another application is satellites. Satellites can be used for communication. They are launched to space, but they revolve around the Earth. So on the right, we have a photo of a satellite. It can receive signals from the Earth and relay the same signal back to the Earth at a different position. That's why they are used for communication. We have phones that rely on the satellite. They are called satellite phones. They don't use a line. Then this is the mathematics involved here. Though this is not examinable, but you should know that the distance between the satellite and the Earth is given by R. G is called the universal gravitational constant. M1 is mass of the satellite. I think here M1 has been used as mass of the Earth, and M is mass of the satellite. So the centripetal force experienced by this satellite, which retains it on its own orbit to revolve around the Earth, is given by G, mass times mass of the Earth times mass of the satellite itself, divided by radius squared, which is distance between the two. Now, since F equals to mv squared over R, we need to find the V, the speed of the satellite. So when we make V the subject, mass of the satellite cancels on both sides. R cancels one of the R's. Then V will be the root of universal gravitational constant times mass of the Earth over R. I think this should be mass of the satellite. Don't know why it's M capital. Let me see. M1 is mass of the satellite and M is mass of the Earth, yeah. So M cancels, so this is mass of the satellite over R. So this is the velocity of the satellite. And sometimes when observed from the Earth through a telescope, the satellite may appear as if it's not moving, but it's moving in reality. Why? It's because the speed of revolution of the satellite and speed of rotation of the Earth are the same. So in that case, we say that the satellite is in a parking orbit. So when you hear of a parking orbit, is an orbit where the satellite appears to be stationary. And in that orbit, the satellite is revolving at the same speed at which the Earth is rotating. So I think that is just for your personal digestion. What you only need to know is an application. One of the application of circular motion is launching of satellites to space. The speed is for your personal consumption. It's never tested. Something that I didn't mention is there's a difference between critical speed and the let's say, let me use this example. Critical speed applies in speed required to retain a body in motion on a circular path. But here, when we talk about minimum speed for the string to remain taut, remember, as you whirl this stone, suppose this is a stone being rotated, you must use a certain speed, otherwise the stone will fall down here if you don't reach that speed. So when you hear of minimum speed for the string to remain taut, this string here, especially position A, minimum speed for the string to remain taut, then it is V equals to the root of Rg. V equals to the root of Rg. But when you hear of critical speed, this is the maximum speed beyond which a body in motion skids out of the road or circular path. Another case applies where we have water in a bucket and then you are swinging it vertically. If you don't swing it beyond a certain speed, then this water comes out. That is the minimum speed I'm talking about. So you can find a question asking you, calculate the minimum speed below which water comes out of the bucket. I think I saw that question somewhere. Let me see if I can trace it right now. Yes, number 19. Number 19 up here. A bucket full of water is whirled in a vertical circular path of radius 1.6. Determine the minimum speed required to keep the water intact. So in that case, you will do minimum speed V equals to the root of Rg. So that V will be the root of 1.6 times 10, which is 4 meters per second. So if you rotate this bucket at 3.9 meters per second, the water will come out. So it has to attain a certain speed. So I hope that is clear. Then we have another application here, number 26. A child of mass 20 kilograms sits on a swing of length 4 meters and swings through a vertical height of 0.9 meters as shown in the figure below. Then determine the speed of the child when passing through the lowest point. So remember, this child is 0.9 meters up. So he has some potential energy. So of course you will say potential energy lost equals to kinetic energy gained. As he moves down, he's gaining kinetic energy. So mgh lost equals to a half mv squared. Mass will cancel because the child remains 20 kilograms. GH equals to a half v squared. Our G is 10. Our height is 0.9 equals to a half times v squared. So that will be 18 equals to v squared. Therefore, v is the root of 18. So velocity is the square root of 18, which is 4.243 meters per second. Then Determine the force exerted on the child by the seat of the swing when passing through the lowest point. So we are being asked, what is the centripetal force at that lower point? Force exerted on the child by the seat of the swing when passing through the lowest point. So centripetal force at that point is the same as the tension at that particular point. So we will have mv squared over r plus mg. So the mass is 20. Our v is 4.243 squared. Radius is 4 meters plus 20 times 10. So we have 5 times 4.243 squared plus 200 gives us 290 newtons. So the force exerted on the child by the seat is 290 newtons. So that's an application question which you need to apply the knowledge of what we have learned. So I think that brings us to the end of this chapter, unless there is any question. If there is no question, we are free to leave. And thank you for attending. Yes,
Teacher,
Mandela.
teacher,
Yes.
I'm just requesting if you could send to us these questions.
Okay, I'm forwarding to Madam Kanyiri. I think did you receive the other notes? Somebody requested for the notes.
Yes.
Yes, I forwarded them. So I'm forwarding the questions to her. Sawa?
Yes, and the recorded lesson also.
That one you will get from her because I'm not the one recording.
Okay, thank you.
It's Washira, Mr. Washira, and Madam Kanyiri who can access it. Sawa?
Yes.
Okay.
Yes.
Any other questions?